Today, we're hearing about the coastal waters. So you've heard from some of the previous lectures that those can be quite tricky and things get quite complicated. So we've got quite a lot to look forward to, I think, in this talk. And our speaker is Dr. Songyun Son. Dr. Son received his undergraduate and master's degrees in oceanography from Busan National University in Busan in South Korea, and then went on to do a PhD in oceanography from the University of New Hampshire. And after a couple of postdoctoral appointments, one of them at the BIO, the Bedford Institute of Oceanography, and I think also at the University of Maine, he went on to join the STAR, which is the Center for Satellite Applications and Research with NOAA. And he worked as a research scientist with Colorado State University as well. Dr. Son's current research is focused on the validation and evaluation of satellite ocean color products from sensors such as VIIRS, if you're familiar with that instrument. If not, we may well hear about it. And that's VIIRS on board both SNVP and the newer NOAA 20 and NOAA 21 satellites. He's also interested in algorithm development and application for the ocean color remote sensing in general, with broader interests spanning monitoring water properties and marine ecosystems using various satellite remote sensing and fee-measured in situ data. Human climate changes are also of interest, especially in coastal ecosystems, and he wants to understand the spatial and temporal variation of phytoplankton productivity at various scales. So I'm sure you will agree, we would be hard-pressed to find a better person to give us this introduction to remote sensing in coastal and inland waters. So it's my pleasure to hand over to Son for the lecture. Thank you, Son.
Oh, thank you very much for your introduction. First, good morning and good afternoon and good evening. I'm very glad to have an opportunity to give a lecture or a seminar. Yeah. Also, thank you very much, everyone, to attend this presentation. Hope it's helpful for you. Let me share my screen. Okay. Okay, can you see the slide?
That's great, Son. Yeah. Okay,
yeah, thank you. My name is Songyun Son. I'm working in NOAA Nested Star, Maryland, in USA, since 2007, February 1st. It's quite long. And as Tom mentioned, I'm originally from South Korea. I came to USA in 1999, and I was working a little bit in the Bedford Institute of Oceanography in Canada with the Trevor and and some other colleagues here. Okay, my talk today is more about remote sensing in coastal and inland waters, focusing ocean color remote sensing. So I think you already had the lectures in previous 4 lectures. Those covered more introductory information about ocean color remote sensing. So I'm not going to dive in. I'm going into some information about ocean color remote sensing, but try to show more research results from my previous study. Okay, before we're going to the coastal inland ocean color remote sensing, I like to share with the information about the satellite ocean color sensors. Some of you are already familiar with these sensors. There are historical satellite ocean color sensors. I think the most important sensor is the CGCS. It's Coastal Zone Color Scanner from NASA. It's on board Nimbus 7, which is the first ocean color sensor operated from 1978 to 1986. And the next important thing, in my opinion, is the CWIPS. That is more practical. The first ocean color sensor launched by NASA and is operated for more than 10 years, from 1997 to 2011. CWIPS data provided a lot of good research products using ocean color data. And there are some other sensors by Japan, OCTS, and GRI, and the MED is also important satellite sensor by European Space Agency. And then the last one is a Goshi one. I think that is quite important sensor in ocean color community, which is the first geostationary ocean color sensor by Korea, which is successfully operated for about 10 years, 2011 to 2021. Here's an example of a coastal zone color scanner. The first ocean color sensor from 1978 to 1986 on Nimbus 7. The bottoms are the example images of from CGCS. Here's current satellite ocean color sensors. There might be some update, but the Goshi 2, the geostationary ocean color satellite, is Goshi 2 replaced Goshi 1, which is launched in 2020. And another important sensor is MODIS Aqua by NASA, which is launched in 2002, which is still operating over 20 years. But as I know, MODIS Aqua is retiring this year because of the quality issues. I think it's sense degradation issues. And there are many ocean color sensors by European Space Agency, Sentinel series, Sentinel 2A, 2B, 3A, 3B. And there's a BIRS sensor by NOAA, which is launched in 2011. BIRS on SMPP. That's operating for about 10 years with MODIS Aqua, so we can transit smoothly. And there are two more BIRS series by NOAA. BIRS on NOAA 20. Actually, there is a JPSS, J1 sensor record. And last year, October or November, the BIRS on NOAA 21, the J2, is launched. So now we can go to the satellite ocean color application algorithms and its applications in the coastal and inland waters. As you may know, there's some applications of ocean color remote sensing. One is for the marine food webs, implications for marine resources, and monitoring or investigating marine pollution and water qualities, and excuse me, ocean productivity and global carbon cycle, ocean acidification, marine biodiversity and function, and validation and improvement of Earth system ocean biogeochemical models, and data assimilation and assessing the marine ecosystem to climate changes. But these are for the global ocean, but also for the coastal and inland waters too. Here's about some differences in coastal inland waters. with the remote sensing. Coastal and inland waters are optically complex, where non-phytoplankton components such as suspended sediment and colored dissolved organic matters, called cedon, are dominant due to mainly river runoffs and shallow bathymetry and tidal mixing. So it is highly required to have reasonably tuned ocean color algorithms for more accurate observations in the coastal waters and inland waters, especially turbid waters. In addition, higher resolution satellite data can help to investigate the finer structures in the coastal environments. In general, polar orbit ocean color sensors has about 1 kilometer spatial resolution, but coastal region is a smaller area and more dynamic, so we need to higher resolution satellite data, such as Landsat about 30 meter spatial resolution, and I think it's Sentinel MSI, and there's a very high resolution CubeSat data. It's Planet about 3 meter, but it's commercial sensor. Yeah, here's examples. As mentioned, global ocean color algorithms are not working very well in the coastal, turbid coastal waters. So here is one example of a water diffuser attenuation coefficient at 490 nanometer, which is called KD490. Some people may not familiar with this parameter. You can see that is water clarity or turbidity related. There are some examples. A comparison matchup between model derived KD490 and in situ KD490. The model KD490 derived using the standard models for the global ocean. So you can see those model derived values is quite underestimated. This one is new inverse semi-analytical KD model for the turbid waters. That is basically for the Chesapeake Bay in the U.S. East Coast, but we also tested for other global coastal waters. So as you can see in the bottom left, bottom images, it's a MODIS derived KD490 images. The left one is using original algorithm. The right one is a new algorithm. You can see the original KD490 values is quite underestimated compared with the new algorithm derived KD490. And the right side is KD490 images in the Amazon River. You can see left and right the KD490 values images with the new algorithm looks more realistic. This one is what KD PA. PA is a photosynthetically available radiation. So you can see there is a visible band from about 400 to 700 nanometer. So there's a conversion algorithm. You can see here is KD pi from KD490. There's one is from clear ocean, but we also derived for the turbid the coastal waters. So we merged those two algorithms for the global oceans. There's various images, sample images in the bottom. Maybe many of people are interested in suspended sediment in the coastal waters. There is one of the examples from my previous research. These are MODIS climatology monthly suspended sediment using the regional algorithms. This is one to et 2005, I think, for the Yellow Sea and East China Sea. So this map shows the seasonal, temporal, and spatial variations of total suspended sediment in the study area. You can see along the coastal area, the TSS is quite high in summertime. In the middle of the, in general, TSS decreased, and especially in the middle of the Yellow Sea, you can see there's reduced TSS values. Of course, outside of the bottom, the south and eastern area, that is crucial current affected area, so TSS is quite low. And right plots are the seasonal changes in TSS for different area for the Bohai Sea and Yangtze River mouth, and bottom twos are the coastal region. As you can see, TSS is quite high during the winter time. I think that is because of strong vertical mixing. And summertime is lower because of stratification. And the bottom right plot is in 10-year variation for about 10 years based on Moody's derived monthly TSS. There is in 10-year variations. This is the diurnal changes of TSS in the west coast of Korean Peninsula. That is from Goshi sensor. So Goshi has the 8 measurement around the Korean Peninsula, Korean seas. So as you can see, a set of Goshi image provide hourly changes in hourly snapshot of TSS. The right figure is we select the 2 coastal region in the Korean Peninsula, the west coast of Korea, with the tidal current with the TSS values from the Goshi. So you can see Goshi derived TSS has a strong correlation with the tidal mixing. Here's another example of TSS, suspended sediment, in the Chesapeake Bay, US East Coast. There are several regional algorithms of TSS in the Chesapeake Bay. So one is based on KD490. TSS in Chesapeake Bay is quite a strong correlation with the KD490. So we derived these equations based on 15,000 in situ measurement and satellite data. So right top images from Moody's derived the seasonal climatology TSS images. You can see the spatial and temporal variations. And the bottom right is the monthly mean Moody's TSS to see the intennual variation in the 3 different bays. So as you can see, there are strong intennual variations which are related to river runoffs and the rains and storms. This one is quite a while ago. We tried to see the decadal changes from CWIPs and CGCS. So the left image is a ratio of CWIPs to CGCS long-term means, 443, NLW 555, and chlorophyll A, you can see there's decreases in 443 and the increase in 555 and chlorophyll A. We also compare with the in situ data, the right side, there's a it's about 20 years 20 to 30 years time series of temperature, salinity, Secchi depth, and zooplankton biomass. You can see there is increasing or decreasing trend. So we can see we can use satellite data, ocean color satellite data. Now we have over 20 years satellite data, which can be used as the climate data record with the CDR. Here's the prime production models in the coastal regions. This one is we used the vertically resolved prime production model by Trevor and Shubhasan-Kedranas in 1988. There's the equation for the prime production algorithm, and we applied this algorithm with some modification or updating, tuning the parameters. So for the yellow sea, there's some example for you to calculate the light with the depths. We used KD490, but KD490 didn't work very well, so we used good relationship, strong relationship between Secchi depths and NLW 555. Also, we tuned some parameters, PB max and alpha B for this study area based on in situ measurement. Here are CWIPs derived prime production, daily prime production within the watercolor using the improved, the modified prime production models. You can see there's differences in May and September prime production in the Yellow Sea. There's another prime production study in the Chesapeake Bay. Actually, there's the paper for the Chesapeake Bay program, Chesapeake Bay production model. It's called the CBPM by Larry Harding, end of 1990s. I don't remember the year. This algorithm is based on VGPM. I tried to implement this algorithm for the satellite-derived MPP in the Chesapeake Bay, but it's quite complicated or not easy to use for satellite data. Also, there are some errors. So, using more updated in situ measurement, we improved this algorithm. Especially use the new derived KD490 algorithm, which can reduce the uncertainties in the coastal area, and it's about 2 to 3 times. And the PB op, PB max, that is derived from many different parameters in the original paper. We simplified that relationship, PB opt, based on temperature, which worked better. So right side, there is a monthly MPP from Modis Aqua. You can see the seasonal patterns, and also they're spatially different, especially in the northern Chesapeake Bay. I mean upper bay, northern upper bay. In general, the prime production is lower. That is because of the light availability. And the summertime usually is a higher prime production. In the bottom plot is annual mean prime production from Moody's Aqua in 2002 to 2011. Is a different base and whole bay, entire bay. You can see there's increasing trend, which would be related to nutrient input in the Chesapeake Bay. Now I want to show some human-induced environmental changes using ocean color satellite data. There is a reclamation in the west coast of South Korea. It's called the Saemangum. There's a big dikes. You can see there's two dikes in the area, which was completed in April 2006. We wanted to see what happened before and after the dike completion. So left one is 2003, 1 year before dike completion. Right side is 2008 in summertime. That is a Moody's derived NLW 645 normalized water raving radiance at 645 nanometer, which can be used index of suspended sediment. So as you can see, there's big changes. You can say suspended sediment decreased significantly after the dike completion, especially inside of the dike. Right side, this plot is monthly time series of Moody's Aqua and BS SMPP derived SST, so sea surface temperature, and chlorophyll and the suspended sediment inside of dike. As you can see, the red line is April 2006, the time of the dike completion. So there's a big changes, especially in the bottom TSS. It significantly decreased the TSS. The chlorophyll is increasing, but SST is similar. This significant decrease of TSS is related to tidal mixing. So after dike completion, tidal mixing reduced significantly. Then suspended sediment concentration is decreased too. There's another example, is an ocean dumping site in the Yellow Sea. Now is stopped, but before there was a dump site in the middle of the Yellow Sea. So that is a snapshot of Goshi derived KD490 from 9 o'clock in the morning to 4 p.m. In local time. Maybe you can see the red line from 10 a.m. and 11 to 4 p.m. You can see the red line. That is the track of the vessels, which is putting the organic matters into the water. But now it's stopped. But you can see that the changes. I like to show some diurnal changes from the Goshi data in the Yangtze River mouth. You can see there's changes. You may not see clearly. I will show the animation in the next slide. In the bottom is diurnal changes in chlorophyll A and KD490 and NLW values. You can see there is the hourly changes from morning to evening, morning to late afternoon. Yeah, here is the animation from previous the slide. Let me see it again. You can see there is a diameter changes which is related to tidal mixing and river runoff. Next one is same day, same time, but KD490 algorithm. That is based on the new KD490 algorithm for the turbid coastal waters, which I already showed in previous slide. So there's strong, clear structures and changes. Yeah, here's animation. If I should make a better one. Yeah, you can see there's big changes. Even in the lake Taihu, you can see the changes from the Goshi images. Next one is one of my current research about hurricane impacts on water quality in the coastal waters. There are sample images. The left one is a hurricane Ian last year, 2022. I don't know, some of you already heard about it. It's a very strong hurricane last year, September. It's October. It's early October. That is the category 4 hurricane. So there's big damages in the Florida coastal region. There's these Beers SMPP images, 7-day composite images before hurricane and after hurricane. The upper image is SST, the bottom KD490. The red circle with the black line is the track of Hurricane Ian. Excuse me. So as you can see, there is a significantly decreased SST after hurricane, and KD490 values significantly increased along the coastal regions. Actually, I didn't add the high spatial resolution satellite images. Actually, I also checked the planet-scope images in the very coastal region. There is well, I shouldn't say, but very beautiful pictures of suspended sediment and sea domes in that area. Right side, this I think it is a modest aqua images for the Hurricane Ivan in 2004 past Chesapeake Bay. The left one is 7 days composite image before and after Hurricane Ivan. SST, right side is chlorophyll A. Similar to Hurricane Ian, excuse me. There is a significantly decreased SST after hurricane, and right side is chlorophyll A. And the right bottom figure is a time series of chlorophyll A, actually fluorescence chlorophyll A, and turbidity measured from NOAA buoy in the west, in the middle of the Chesapeake Bay, very coastal region. It's a stingray point in Chesapeake Bay. So you can see, for example, in turbidity, the red line is a hurricane passing date. So after hurricane, the turbidity significantly increased. So it goes about 10 days or 7 days after it's turning to normal. Excuse me. I think Zema presented her research result about COVID lockdown effect in the Indian coastal region. Actually, I also, we had my colleagues in Korea, and I did a similar research for the Yellow Sea. Actually, this is impact on spring phytoplankton bloom in the middle of the Yellow Sea. Actually, in the Yellow Sea, this area strongly influenced by yellow dust and micro dust actually from the east coast of China. There's a lot of industries. So after lockdown, it's all stopped. Then the pollutant nitrogen input is significantly reduced. Then phytoplankton size decreased in the area. There's the plot comparison between chlorophyll A in 2020 and mean chlorophyll A between 2015 and 19. So I think it will be interesting to check the after the lockdown finishes. Excuse me. There's this one is the water quality in inland waters. For example, I'm going to show the result in the Great Lakes in the USA, chlorophyll A and turbidity and saké depths. This is a regional turbidity algorithm in the Great Lakes. The top left plot is comparison between in situ turbidity measurement and Beer's derived KD490. We tried many different things, but there is a strongest relationship between turbidity and KD490, and we derived a very simple empirical algorithm, and it works reasonably well in the 5 Great Lakes area. Using the regional algorithm, we derived the Beer's turbidity images from 2012 to 2018. There's this monthly climatologic images of turbidity in the whole Great Lakes. You can see there is the differences, especially in the Lake Erie, the red part, small one. There's very shallow bathymetry. It's a picture. I mean, the water properties are quite different from the other 4 Great Lakes. Next one is a chlorophyll A algorithm for the Great Lakes. There are some papers. The NASA standard OC3B algorithm is not working well in Great Lakes. There's systematically biased. Then there are several regional algorithms for the Great Lakes. But all algorithms are based on different data set and approaches different. So we tested using more in situ measurement, but we found the standard algorithm is biased. Also, there's some issues in the regional algorithms for chlorophyll A in the Great Lakes. So we tuned to derive the better the OC algorithms. There's equations, and we tested it works quite well in the Great Lakes, and generated the Beer's SMPP chlorophyll images. Just one example, as you can see, the winter time, the chlorophyll concentration is quite low. The spring and summertime is higher. Especially, you can see the very high chlorophyll A concentrations in Lake Erie. It's a red one. Especially summertime, August and September, chlorophyll A concentration is very high. That's because of cyanobacteria bloom. Because annually, every year, there is a strong cyanobacteria bloom in the summertime in Lake Erie. There's another water quality parameters, the Secchi depth. There was Secchi depth algorithms based on NLW or RRS 551 or 550 nanometer. So we also tested and input data a little bit different. We had improved the Secchi depth algorithm here. It's also a simple empirical algorithms. And we generated Secchi depth images from the BS SMPP. The pattern is similar to turbidity. The very shallow Secchi depths in the Lake Erie, especially winter time. I think that is because of the vertical mixing. And Lake Superior, so you can see in December, there's no valid fixed. That's because of the severe weather, like the very strong windstorm and ice covered in the area. There's another algorithm for the harmful algal bloom, the red tide. In Korean coastal area, every year there's a red tide. So this one is there's a very special event in 2013, I think. It's the east coast of South Korea peninsula, the southeastern area. There's a very significant red tide. We compared the images, the OC2C, this Gaussian images using standard Gaussian chlorophyll algorithm. You can see the pictures, but when you see the scale bar, the chlorophyll concentration is about 2 to 3, which is it's similar to just a normal condition in spring bloom. But in situ measurement, they show the chlorophyll concentrations is over 100, while the maximum is about 400, 500. So we improved the chlorophyll A algorithm for the red tide based on 680 and 490 nanometer data. And the right side, new derived chlorophyll A images shows quite high concentrations, which is similar to in situ measurement. Also, there's diurnal changes from the Gaussian derived chlorophyll A using new algorithm. There is diurnal changes from morning to the afternoon. Usually, chlorophyll concentrations are higher in the afternoon. And the right side, we try to generate hot warning index. So it can be used not forecasting, but near real-time forecasting or monitoring using satellite data. Here's one example of a phytoplankton size composition using CCI, OCCCI from 1998 to 2018 or sometime. This is not really coastal region, but including coastal region, that is northern Bering Sea and Chukchi Sea. This image shows dominant phytoplankton size composition for 3 different phytoplankton size: phytoplankton, blue, nanoplankton in green, and red plankton. Red is a micro phytoplankton. So you can see in summertime, usually phytoplankton is dominant in the middle of the Bering Sea area. Next slide is about 20 years time series of the annual the dominant of the phytoplankton size composition, the annual mean in the summertime. The 3 different areas, one from north to south. One interesting is in the northern part, the SST is increasing trend, and microplankton is increasing, but both the phytoplankton and nanoplankton is decreasing. In the south part, the sea, you can see SST is increasing, but phytoplankton is increasing, but nano and microplankton is decreasing. So we can see the phytoplankton size composition is respond to the warming in that area. This is an example of a habitat suitability index for the fisheries in the Korean waters. This HSI index for the left one is Japanese common squid, right one is chook mackerel. This index is based on primary production from the ocean color satellite data to detect and forecast fishing ground information to understand the recent changes in fisheries resources. This one is it may not be related to coastal region, but that is chlorophyll A derived from NDVI in the tidal Platt using Landsat 8 data. So there is a strong relationship between chlorophyll A and NDVI in the tidal Platt. So there are some examples. We are going to try to estimate the time production in the tidal Platt using this information. I mentioned in previous slide, we need to higher spatial resolution data in the coastal regions. These are some examples of high spatial resolution. The Landsat 8, the left one is a suspended particulate matter, TSS, suspended sediment in the very coastal region. And the second one is one sample images from Seahawk, which is the first CubeSat. I think it's about 100 meter spatial resolutions. I'm going to show the information about that. And the right side, upper images of PlanetScope 3 meter images, or RGB and suspended sediment. You can see there is a red spot in the upper images, which is the ocean wind farms in the Korean coastal region, and the bottom is SPM images. You can see the tailing from the wind farms. And right the bottom is one of the example from PlanetScope 3 meter data, which is the seaweed aquaculture in the Korean coastal regions. In Korea coastal region, a lot of aquacultures. We can see the seaweeds from the very high spatial resolution satellite data. I showed some examples from my previous study, algorithms and applications in the coastal and inland waters. So I'm trying to show some future sensors and see the applications, what it can do with the future sensors. Maybe this table not updated well, but there are some scheduled satellite ocean color sensors. As you may know, the red OCI PACE sensor will be launched this year or next year, which is a 1 kilometer spatial resolution, but it has 186 bands from 350 to 2250. And there's another one, SBG, and Glimmer, and BS sensor. BS satellite will launch it continuously. And maybe other people also know about the sensors, future sensors from other countries. Here's different sensors for future compared with the traditional polar orbit ocean color sensors. The PACE, as mentioned, which is a hyperspectral radiometer from UV to near IR at about 5 nanometer resolutions. This sensor, this satellite will be launched this year or next year. And another one is SBG, surface biology and geology sensor, hyperspectral radiometer at 10 nanometer with a high spatial resolution, is about 30 meter. This sensor more focused on inland and coastal ecosystem, but I don't know if this sensor is approved or not. The NASA JPL, I think, and colleagues are working for this sensor. Another one is Glimmer. I think it's approved before pandemic, but I don't know when it will be launched. I think that is this one could be the first geostationary ocean color sensors in USA. It's about 15 times per day, and the hyperspectral ocean color radiometry, but it covers US coast and Amazon River and focusing more on coastal ecosystems. The other one is GeoExo. NOAA also approved to launch geostationary ocean color sensors. NOAA already has more than 10 geostationary satellites or focus on the meteorology, it's a SST or temperature. But NOAA has a plan to launch geostationary ocean color sensors, but it will be about 2030 around to observe ocean productivity and ecosystem changes, coastal inland water quality, and coastal hazards. Here's a small size satellite. It's called CubeSat. I already showed I mentioned the Seahawk. That is first ocean color CubeSat launched in 2018 December. Very small weight, is about less than 5 kilometer, and 18-day repeat orbit. It's about 120 spatial resolutions. The right bottom is the example of the Seahawk CubeSat images compared with the MODIS. But there are a lot more CubeSat images, but from commercial sectors, as I mentioned, the PlanetScope. Nano satellite or CubeSat, which is relatively very cheap compared to the polar orbit sensors, and a small size instrument and high spatial resolution. This is 100 for Seahawk, but commercial sensor has about 3 meter or 1 meter, so you have to pay a lot of money. And CubeSat, we can launch multiple satellites in the same time, which can lead to coastal inland water absorbing paradigm. Okay, with the future sensors, what we can do, we can reduce uncertainties in and improve or develop robust ocean color algorithms, especially in the coastal waters, such as phytoplankton pigment communities and coral reef functional diversity, etc. And productivity and carbon assessment in coastal marshes, tidal Platt, and wetlands. And we can improve the detection of water quality, harmful algal bloom, microalgae bloom, and oil spill accidents to enhance the monitoring system and quantify vertical transport of carbon, nutrients, and oxygen due to the diurnal vertical migration of phytoplankton aggregations. And we can use the satellite data for the fisheries aquaculture site selection tool and advanced remote sensing of marine debris and microplastic, which could be very challenging. I think this is, yeah, I'm done. Please, if you have any question, let me know. We can discuss about it. Thank you.
Thank you, Son. That was a very interesting lecture with a lot of information. As with most of these, I'm sure a number of people may, when the video is available, go back and relook at many of those points because there's a lot to take in. So thank you very much.
Okay, thank you. Oh, do you want me to stop sharing or do you want me to?
I think leave it up. We might come back to some of these slides when we while we're discussing the question.
Okay, yeah. Let me stop sharing.
So as usual, the first couple of questions I'm going to answer myself because those are about technical stuff. There was a couple of questions about the recordings of the webinars. So yes, we do record attendance. That's so that we have numbers on how many people have attended and if people have attended enough lectures to get the certificate at the end of the course. Okay. And also the link for the YouTube channel we can put in the chat now. I think Hannah's, probably put that in. So if you do want to subscribe, get notifications when those videos are available, just go to that site. Okay. On to the contents of the talk.
Okay. Also, you can share my slide. As you know, I already uploaded the PPT file and PDF file. So for PPT file is
I'll put those in a repository.
Okay. Yeah. Thank you.
So we've had quite a few questions coming in during the talk. So we'll try and bunch them by topic. There were a number of questions around the different criteria or what distinguishes things like meteorological satellites for the ocean versus the coast, and what we mean by high fidelity and the requirements on things like signal to noise for some of the algorithms that you've shown. And I just think it might be good if you could go into a little bit more detail about, the difference between really the signals that you're detecting in the coastal ocean versus, say, the deep ocean and the requirements, and why that means you can use something like MSI, which maybe has a higher saturation limit or a different dynamic range to, say, Ulchi.
Yeah, actually, I'm not expert in more technical stuff in the sensors, but as I know, the sensitivity is very different between ocean color sensors and other sensors like meteorological and land sensors. So I think about, well, actually in NOAA, there are the meetings among other scientists from ocean color and SST and atmospheric and land people. the focus is different. For example, the if the error is 2%, is acceptable for atmosphere and land paper. For ocean color area, it should be, for example, 0.2% acceptable. So I think, as you mentioned, the sensitivity is quite big issues. So, but previous Landsat data may not be easy to use for ocean color remote sensing study. Since Landsat A and current PlanetScope, I think last year the the PlanetScope launched the 8-band satellite. Those could be it's, applicable for ocean color remote sensing. But for your
I guess that's part of the difference between, say, PACE and Glimmer.
yeah.
You know, one is designed to look at the coastal zone, which, so they're both hyperspectral, but one
Yeah,
will
yeah,
be
yeah.
looking at the coastal zone, so potentially brighter targets, whereas one is looking at the more deep ocean, which is much darker targets. So they
Right.
have to tune themselves to get the best dynamic range in their respective areas.
Okay, yeah.
We had quite a number of questions asking a little bit more detail about the KD, so the attenuation algorithm.
Yeah.
I think you mentioned a number of algorithms, and I was just wondering if it might be good if you go back over maybe how the algorithm works, but
Yeah.
you can also maybe add in a little detail about the difference between empirical, semi-analytical models, because I think that might be a difference that some people aren't sure or familiar with.
Oh yeah, actually semi-analytical algorithm is empirical algorithm too, right? Because all based on empirical data, empirical relationships. So, although some scientists think, oh, we have to use semi-analytical algorithm, which is much better than empirical algorithm. But when you deep inside, it's still empirical. Without empirical relationship, you cannot make it. Yeah. But how could I say? Yeah. Well, it's ocean color algorithms. For example, it's Chlorplay, KD490, more based on the band ratio. So in general, KD490 algorithm for the global ocean is based on 490 and 550, around 550. So the ratio doesn't detect the big signals in the coastal region. So instead of 550, we use the red band the data, which detect the more signals in the coastal waters, but which may not be working well for the open ocean. So we merged the two algorithms, well, even if I didn't show the information. So basically, this KD490 algorithm for the turbidity water, coastal waters, is use different band ratios using red band. But this is based on mostly the instrument measurement from the Chesapeake Bay. So different area could be really different. But we tested using in situ data from seabeds before, so it worked better compared with the standard algorithm. Okay.
Would it be helpful if I added? Sorry, would it be helpful if I added something about something more about why we might need different algorithms and empirical, analytical, and so on? So if we are talking about analytical or semi-analytical models, we are talking about a class of models where we invoke the principles of radiative transfer to try and understand how the remotely detected signal will behave when there is a change in the concentration or type of the constituents that are present in the water. So you have to go through a radiative transfer model to come up with an analytical algorithm. But as Son mentioned, you always hit against some empiricism creeping in because you need observations to establish the inherent optical properties. Then we need observations to decide how the inherent optical properties, such as absorption and scattering, will change if you change the concentration of the substance. For example, the phytoplankton concentration or the types of phytoplankton present. So because of the complexity of the optical problem that we are dealing with in remote sensing of ocean color, especially when we come to coastal waters, it is difficult to completely avoid the need for direct observations to anchor your model and to improve the interpretation. But having an optical radiative transfer based model in your back pocket should always help you to understand how you expect the algorithms to behave, how you expect the algorithms to break down under the conditions you are wanting to apply it for, or for the region where you want to apply it for. So the best approach to remote sensing of ocean color is to juggle the two. To ask yourself, what do you need observations for to calibrate your model? When do you need to revert to a totally empirical approach? And even if you do an empirical approach, when do you expect the algorithm to perform well? Think about when the algorithm might actually break down and you might need another algorithm. I'll stop there.
Thank you for excellent explanation.
Thank you, Shubha. While we're on the topic of algorithms, there were a number of questions, I think, relating to Gochi, which you showed quite a lot of data from, asking about which chlorophyll algorithms you had used or would recommend, and how well they were performing. I think that's a sensor that's not so familiar to a number of people.
I mean, Gochi chlorophyll algorithm for the red tide or just in general?
I think the general one, but also, I mean, the red tide you showed, I think other ones that might compare, like OC3 or something like that, you know, there's other applicable algorithms, right?
Yeah, actually, OC3 algorithm for Gochi data is for the whole area, but as some of people may know, the Korean world is quite complicated. The west part is the Yellow Sea, and it's the China Sea and Bohai Sea, which is very very turbid and complicate the ocean waters. But eastern part is the Japan Sea, is a more clear water, and the southeastern part is a Kuroshio region. But another issue is that areas influenced by the yellow dust, so it could be a little different. But in general, the algorithm, the chlorophyll algorithm, based on OC3, but in the west, the Yellow Sea and East China Sea, there's another regional algorithm. It's called the YOC, or Yellow Sea Ocean Color algorithm, derived by many scientists from Japan, Korea, China. So mostly people, I mean, local people using that algorithm. So for the CEO of Japan, so actually I lastly, early this year, I published one paper, which is the improved chlorophyll algorithm, because we found the OC3 algorithm is biased in the low chlorophyll concentrations. So we improved. So well, for maybe we need to use a different algorithm for different area. But yeah, I didn't start, but I'm thinking to merge those algorithms, how to merge those algorithms without, the boundary between the area, the different waters areas. Yeah.
I think that if you're not going to show slides at the minute, Son, if you stop showing your screen, then people will get a slightly bigger view maybe of a discussion.
Okay. Yeah.
The issue, I mean, I think it was clear from your presentation for each of the products, there's a lot of regionality.
Yeah.
And there's a lot of tailoring. I think it's right. We've had people ask about whether algorithms that you showed were applicable to all areas or other coastal areas. And I think often that comes down to if the waters in that area have similar properties. So one approach is that I'll cover actually in the climate data series about merging records and merging algorithms. Will go into how you, or possible methods for blending algorithms. But really, I think it comes down to in situ data and being able to validate whether or not that algorithm is suitable, right?
Oh, I just missed you. Do you want me to share presentation?
No, that's fine. That's fine. That's fine. No,
Okay,
that's
okay,
fine.
yeah.
But yeah, I was just saying, I think so. If someone wants to take one of these algorithms and try it for an area themselves, or wants to choose which algorithm to use, they either need in situ data with which to validate the approach,
Right.
Or assess, compare the approaches, or they need to have some reasoned understanding of which of the regional algorithms is most suitable because their region is similar to that region, be it CDOM dominated, sediment dominated, whatever it is.
Right. Actually, basically we need to test, validate the algorithm for their own study areas, because as we mentioned, it's all different water properties, especially in the coastal water.
One question that came up, and I think it's certainly an issue more for the coastal zone than as deep ocean specialists, but the issue of bottom reflectance and how you might deal with that. Is that an issue in your work?
No, actually, bottom reflectance. There's a studies for the clear ocean waters. Usually, it's the coral related things. I think there are several papers for the Florida coastal regions where it's very clear ocean waters, but for the turbid ocean waters, I don't think the bottom reflectance is issues, because already it's very turbid. It's not easy to get the signal from bottom. So, but yeah, for the coastal region, we don't really need to turbid coastal water. We don't really need to worry about bottom reflectance, well, in my opinion. But the clear coastal waters like Florida, the coastal region, or there's a great the reef barriers in Australia, but there are several studies, as I know.
Yeah, and I think this is one of those cases where it stresses again, remote sensing provides an incredible ability to view large areas over relatively short repeated timescales, but you cannot take away the value of in situ data for validation and checking. So it's a good point to make. We did have a question when we were talking about some of the constituents of the water earlier about the terms SPM and TSS and whether those are different. So obviously we've got total suspended sediment or suspended particulate matter. Often those are interchangeable. The other related term that people shouldn't conflate or swap in is turbidity, which is not a concentration, but that is a measure of clarity. So just for those that may be confused around those terms, often the suspended matter, or be it total suspended matter or suspended particulate matter, is a mass concentration, and those are roughly equivalent or alternate terms for the same thing. But turbidity is different. That's something.
Right. That's great. Yeah, TSS and TSM or SPM, I think it's they used to. I think it's almost the same, but turbidity is different. Also, there's a water clarity, but I think it's inland people use water clarity rather than turbidity.
Okay, so another question. We've got a lot of good ones. There were a couple of questions around Secchi depth. I think I'm not sure if we already had that described in one of the other lectures, but there was a request to estimate the process of deriving Secchi depth and KD 490 given a set of reflectance data. So how do you go from reflectance through to the KD and the Secchi depth? Because Secchi is obviously a human interpreted visual.
Right. Yeah, actually, personally, I prefer KD 490 or turbidity rather than Secchi depth. But there are many studies about Secchi depth, where I also similar. How could I say? I agree to the question. Secchi depth is more from visual inspection rather than real measurement. So, but I don't know. But there are some requests for Secchi depth products. Some people, want to have a Secchi depth product. So I think that's why.
And those are usually empirical algorithms then to get it from
Right. But yeah, as you know, the Dongping has more, analytical types algorithms, which are used for global oceans. But so for this case, in my case, is for regional algorithms.
You're muted, Shiba.
Yeah, Shiba is good.
Sorry, I think in Europe, one of the requirements for reporting on water quality is to report on Secchi disk.
Nice.
So it has it also has the advantage of being one of the oldest optical instruments that have survived the test of time. So if you want to ask yourself what was water quality like 100 years ago, the chances are that you might find Secchi disk measurements, but no satellites, of course. So it has this advantage of being something you can rely on if you want continuity. And because of that, and also because there are several studies, as Son mentioned, that relate Secchi disk to optical properties through radiative transfer, they also can be, to some extent, related to more rigorous optical measurements. The difference is, as both of you have been mentioning, for Secchi disk measurements, the instrument is the human eye. So it is not influenced solely by the radiative flux, but it's also affected by the spectral response of the human eye to various wavelengths. So there is always a level of human-related error in circuitous measurements. So if you think of circuitous measurements as something that is very simple, but that can be done by just about anyone with a little bit of training, then you can also improve to some extent the precision of the measurements if more people use it and more people report it. In one of the lectures to come, I think in about 3 weeks' time, Grinson George will also talk about how SekiDisk is now a citizen science tool. So that explains why SekiDisk is also useful as a tool for filling gaps when, because of clouds or whatever other reasons, you miss satellite data. So it continues to be an instrument that is still very useful today.
Yeah, actually, similar to what Shuba mentioned in first, actually, in USA, I think in ocean color community, they think more about the measurement, it's visual inspection. But for example, in the coastal area and inland waters, like Great Lakes, different agencies involved, like not only NOAA, but also EPA, US EPA, Environment Protection Agency, and the USGS. So their focus is different. So that's why, as Shuba mentioned, they require SekiDepth because those people, inland people, oh, we need to SekiDepth. They all, so that's why in the monitoring data sets from NOAA, USA, EPA, they include the SekiDepth all the time.
We've had a number of questions around primary production. I'm going to try and wrap them all up into one question, really. But the first question was, is chlorophyll always related to primary production? And I think the short answer is yes, because it's the primary photosynthetic pigment. So it's very, very strongly tied to the light harvesting. We can go into more detail as a panel on that, but that's the short question. And then moving on from that, there were questions around how sensitive things like primary production algorithms are to atmospheric correction. And if there are multiple algorithms, how do we select the right one? Are they regional? And I think this leads us into a bit of a discussion around when you're choosing algorithms, say for primary production, and considering the level of uncertainty that is acceptable. So as we said, when we start at the top of atmosphere radiance, we might need a sensitivity of less than 1% or a few percent because we're trying to extract a very small ocean color signal. Once we get down to reflectances, I think the GCOS requirements are around 5%. And for chlorophyll, it's around 30%. So if we're saying that we are happy with a chlorophyll product of 30% accuracy, we can't expect a primary production algorithm to have a 5% accuracy. So that's where it comes in. So there is a sensitivity, but if we get the primary production right to 30 or 40%, I think that's pretty good. So that's my kind of question for the panel is, with primary production, what are the most important factors, and how good is it between regions and global estimates? I think would be the
well, I think it's a very hard questions to answer. But here, Shuba and Gemma, they are more expert than me in primary production algorithms. But I don't know. It's there are many algorithms. I prefer Trevor and Shuba's algorithm personally, but many people are using BGPM. That's because, in my opinion, very easy to use. Just very simple line, simplification. Well, some people say, oh, it's very complicated too, but I don't really think it. So also another thing is, the Shuba's the prime production algorithm sometimes they need to calculate the vertical parameter. So also just but seeing they say, oh, equation, I don't like it. That's why they don't use it. But I don't know, which one is better, but all depends on the users. Yeah, you can maybe Gemma Shuba can explain.
Yeah, I can add. Well, I totally agree that some of the primary production models are more easy to use. So lots of people opt for the easy to use one. And what TJ pointed out as well is that it's important to consider what you're after. So these primary production models can be depth resolved or not, wavelength resolved. They might have a chlorophyll A profile or assume a straight chlorophyll A profile. So it's really, you need to sort of look into it a little bit and think about what do I need, what do I want to study, at which resolution. And then TJ also pointed out that you have to consider the uncertainty, which is something that's not often provided with primary production models. I think the community is working quite hard on that to provide with the primary production estimate an estimate of the uncertainty. So you can choose for your area the primary production model with the lowest uncertainty. So maybe Shuba wants to add to that.
Well, we will also have a whole lecture on primary production,
Yeah.
I think, later in
Yeah.
the course.
If
So there will be
could,
more.
yeah, it's true. When is it, Tom? There is a whole lecture on primary production. We can address some of these things at that time as well. But I want to add one point. I have been working on this, I've just counted maybe 35 years or something on primary production models. And I always get asked this question, which one is better? And it is a question that I have refused to answer for 35 years. And I will refuse to answer that question now. It's not for any other reason than this, that if you are a scientist, you have to develop your critical faculties. You have to ask yourself, why do I want to do this? And which method or which approach or which product suits my requirements best? And if you want to be able to answer that question, there are no real shortcuts. You have to study the methods, you have to study primary production, and you have to develop your faculties to a level where you can answer that question. You will not get it from me. But I will tell you my approach, that when I do my work, I try to do the best I can. And if there are other papers that come along, I try to read those papers and see what is there in their work that I can borrow, because they are doing it better than me. So I can make my work better. And I hope that that is a philosophy that all of you will find is an acceptable one. But you will learn more about primary production in the third set of lectures.
Yeah, I think, and I hope that students see across this course, there's so much science going on, and often it's on those borders or interactions between groups or between communities that the most progress happens, because you can share ideas. So yes, very, very nice points, Shuba.
Well, by the way, one difficult thing is currently people don't really measure prime production because it's very difficult. It takes time and it's hard. So yeah, especially the C14 or C13 cow-based prime production measurement is very limited. So it may not be easy to improve prime production algorithms. But this is my personal opinion.
There was a couple of questions around the HABs images that you showed. There was a quick one, I think, which was for your HAB warning images. Is that threshold based?
Oh yeah, actually, in Korea, I think it's a Fisheries Institute. They have some threshold for the warning and now warning and there's the pre-warning, that kind of index based on cell size. So there's a relationship between cell size with the chlorophyll concentrations. So from in situ measurement, So that warning map based on the chlorophyll concentrations with the threshold concentrations. Yeah. That's what I have done.
Thank you.
Can I ask that?
Yes.
One more question, related one to Son. Son,
Yes.
you were talking about red harmful algal blooms, right?
Red tide, but also people.
Yeah, but
harmful algal bloom help. Yeah.
At that, for implementing that one, did you develop algorithms that are tailored for red tides?
Yeah, actually, based on in situ optical measurement and the chlorophyll concentrations. Yeah, actually, there's a very severe event in that time. So many people went to the ocean to measure, and we used those data.
So that's different from a simple threshold algorithm, right?
Oh, you mean the warning algorithm?
For the red tides, yeah?
Oh, yeah, actually, that is for that species in that area. But almost every year, there's a harmful algal bloom along the coastal area, especially south coast of Korea. But this part is more the Japan Sea area. The species could be similar, but not exactly the same, as I understand. Well, one thing I'm trying to do is apply that algorithm for the CCI, OCCCI data to see the any changes in the harmful algal bloom in that area. But yeah, well, it's a different issue, but I can discuss that.
I'll be interested to see the results.
Yeah, but I can discuss with you and Shuba later about OCCCI data. I have some difficulties. I mean, I can simply use, but I just want to have some.
For the while we're on the latter set where you were looking at some of the more let's say non-standard products of harmful algal blooms and phytoplankton groups and things.
Yeah.
There was a number of questions around estimating phytoplankton size class.
Yeah.
And there were queries around the approaches and the language, the coding languages used and this kind of thing. I mean, the coding language, these algorithms, once you have them from papers or they're published, I mean, we have ones we run in Python. I don't know if you do the same, but you could run it in any language really you choose. But I was just wondering if you could go into a bit more detail about, with your map of the micro, nano, pico, what the methodology for that was in relation to maybe other group algorithms.
Yeah. Actually, I didn't develop the PSC algorithm for the area, but I just simply used the existing algorithm. Actually, that algorithm based on Takafumi Hirata. Actually, he was working in PML. So I think the Taka with Jim Akins, this basic algorithm. I used that algorithm because we didn't really have a complete set of optical data. So my colleague has just the RRS data and the 3 different size data, the chlorophyll data. So that's what I simply used. But it looks quite well in the paper I already mentioned. So I used, I think that was 2007, the paper. It's quite simple, the empirical algorithms based on sea dome absorption. So I used that algorithm. So I didn't develop the algorithm. It's quite complicated. Also, there are many different types of algorithms. I think Shuba also, yeah, started.
There's also
yeah,
there's Bob Lewin and others who've
PFT,
done the
yeah.
micro code. Yeah.
Okay. Another thing is, I used the idea, kind of old generation, not really old, but yeah, I don't. Yeah, I need to use switch it to Python. Yeah, so I use most of my work is based on idea and CDAS.
Okay. I think you can probably fit one or two more questions in. I'm just keeping an eye on time because we do have a hard cut off at the end of the session to other meetings. So, there was a question around comparing Gochi with other polar orbiting ocean color satellites. Do you know of any good references, for example, where people might be able to see the cross-validation of Gochi with other sensors?
Yeah, I think there are several papers, but as you may know, Goshi data actually is processed by KIOST, the Goshi 1 data. Goshi 2 is different. I mean, different agency reading Goshi 2 data, but Goshi 1 data is originally processed by KIOST, satellite center, but also there are different products. So NASA, OBPG, they have a contract with the Korean KIOST, so they download all Goshi data and process. They already uploaded in NASA OBPG website, but also NOAA, I mean, now I switched to a different group, but my previous group has all level 1B Goshi data, and we processed them. So I compared those three products. So NASA processed Goshi and NOAA processed Goshi data is quite similar. But KIOST processed Goshi is really different. I don't want to say which one is better, but there's some limitations, I think, in Korean side. Yeah, there are papers, so I can provide the information. Yeah.
It's more to do with the processing than the sensor itself.
Yeah. I think the algorithm is different.
Okay.
Another thing is, the paper which published for Goshi data is for NOAA processed Goshi data. They used the atmospheric correction algorithm based on comparison between Goshi and Beers.
Okay.
Data, I think so. So you can use.
While we're considering Gochi and Veers, so Veers being polar orbiting and Gochi being geostationary.
Yeah.
Obviously, when you're doing matchups with Gochi, you can get quite a close time matchup because
right.
For Veers, you've got one overpass time, and you might take measurements at different times in the day, and the coast is very dynamic.
Right.
What sort of time limits do you put when you're trying to get your matchups in these coastal areas?
I tested it before, but it tried to use data around noontime, 11 to 12 o'clock. But even if not considering the dynamics in the water, but in the early morning and late afternoon, I think the data is quite different. Maybe that's because of the atmospheric correction, and especially in the 4 p.m. data, especially winter time, data is quite overestimated. So that's why I
So
don't
you're trying to
really.
get an hour, only an hour of overlap between or offset
Yeah,
between-
around the noon time is better. Yeah.
Okay. All right. I think we might start to wrap it up there. Maybe if there's one quick question I can find. Answer those. Well, we've had someone ask if they can work with us to validate products in their coastal areas. I think if you have monitoring stations or any sort of in situ data, feel free to reach out. I can tell you the ocean color community is very friendly and happy to discuss data and validation, so and algorithms. So please, yes,
Yeah,
that would be good.
actually, yeah, that would be great.
And with that, I think we'll wrap it up there. And thank you again for the presentation.
Oh, thank you very much for your attention, and I was very glad to have a chance to give a lecture. Okay.
Thank
please
you
let me
very
know
much,
if you have
Don.
any-
Thank you all for participating.
Okay, yeah, thank you. And if you have any question, send me email. That'd be great. Okay. Thank you. Bye.